Welcome to the second screencast on recursion for ICS 211. So last time we talked about what recursive thinking is and some basic recursive problem solving. Today we're going to talk about recursive data structures and some more problem solving and some examples. So we can and we often do define data structures recursively. For example, the data structure is empty, or the data structure has a reference to a version of the data structure. For example, the linked list is considered a set of nodes, so the linked list is a node followed by more linked lists, so the head may be null, or the head.next points to another linked list. So we sort of have this base case that the linked list is empty, or head points to a linked list. And that's how we can define a linked list. So it's a linked list is a head that points to a linked list, or the head may be null. So if we think of the linked list recursively, we can write our methods for manipulating a linked list recursively. Now, in order to do this, we have to write a helper method, a recursive helper method. So the size method that returns the size of the linked list calls the recursive side, the helper method, with the head of the linked list. So we're going to use the size that takes a node as our recursive method that will actually do the counting of the size. So if the thing that is passed in is null, we return 0. Else recursively, we do 1 plus the size of head.next. This is very similar to the way of counting the size or the length of the string that we did last time, where we're just going to say, I'm saying I add 1 plus however big the rest of the list is. And so eventually we'll get to the end of the list where head is null, we return 1, and we'll have the activation stack to keep track of how many times we had to call size. The recursive size that actually does the counting when we return when we combine them together. So we can do toString very similarly, where we have the public toString method calls the private recursive toString method with the head, which is the beginning of the linked list. The recursive method is private. It takes a node. If the head is null, we return the empty string. Do have a typo. That int should be a string, sorry. Else we return the data plus a space plus the toString of the rest of the list. So again, we'll call toString again and again and again until we get to the end. Then we return an empty string, and then we'll append that to the head.data, and we'll keep building back the string, and then we'll correctly produce a toString representation of the linked list. In the textbook, they use a /n, a new line. I prefer having my toString on one line instead of vertical. I like it horizontal. I find it easier that way to look at. The replace method replaces an object in the list with a new object. In this particular version, we're going to replace all occurrences of the old object with a new object. Again, the public method calls a recursive helper method, and we add the additional information of the node we're processing. So we start with the head, and if the head is not null, if it is null, we're done. We've got to the end of the list. We don't need to do anything. And since this is a void method, we don't have to do we have no returns. We just don't do anything. And so we first check to see if the old object equals the data at where we are. If it does, we replace the data where we are with a new object, and then we continue on because we're going to we got to check all the items in the list. So we recursively go to the next item, and we call the replace method on the next item in the list, and eventually we'll get to the end where the head is null, and we will stop, and we're done. We're done because we don't have any combinations. All the old objects have been replaced with the new object. So the next method is to add. So we want to add at the end of the list. Now with this add, the public method, we have two cases. One If the list is empty and the head is null, then all we do is we set head to a new node given the data. If the list is not empty, we need to get to the end and add the data, a new node to the end. So we call the helper method, the recursive helper method, with the position, the beginning of the list, and the data. The recursive method says where are we in the list, we get the data. So if head.next, so the next item, so we're pointing at the last item in the list, then we create a new node and make that the last item in the list. And that's why we do head.next. And we know that head's not null because the public method checked for that. And we're checking to see if head is next is null, so we're never gonna put null in this private method. Else we go to the next item and we're gonna say add the data to the linked list defined by head.next. So again, we're just recursively going down to each next linked list, and eventually we get to the end, we add the node at the end. Remove is slightly more complicated because again, the remove, we need to have a couple other cases. For example, in the public one, if the list is empty, we can't remove anything, so we return false. And then we have the special case that the head is the thing we're removing, so we need to just do head equals head.next, so that skips over. We removed the data from the head, and we removed it. Else, we call our recursive method, and in the case, because it's a singly linked list, we have to keep track of not only where we are in the list, but the predecessor to where we are in the list, so that we can move the predecessor's next over to our next to pull our data out of the list. And that's why we have the head, the current node we're looking at, and that node's predecessor. And that's why when we call remove, we say the thing we're looking at is head next, the predecessor to head next is head. So we then check to see the thing that we're currently at. If it's null, we've got to the end of the list, we did not remove any data, we're done, we return false. Else, if the head.data equals the thing we're removing, we need to make the predecessor's next point to our next, head's next, to skip over that node. So that is removing the head node from the linked list, and we return true. If the data is not what we want to remove, we move on to the next node in the list until we get to the end of the list. So we recursively move on to the next node. Back to recursive problem solving, we'll talk about how we design the problem solving solution. You break up the original problem into a base case or cases that you can solve easily, and then you break up the problem into smaller versions of the original problem and you solve them recursively and then combine the results. For example, the Tower of Hanoi problem, classic puzzle game. You have some rules that say only the top disk on a peg can be moved and a larger disk cannot be placed on top of a smaller disk. So what's the recursive solution to this problem? You normally have 3 pegs. You need to move the tower from one peg to a destination, the start peg to a destination peg. So the recursive solution is if the number of disks you're moving is 1, you move the disk from the starting peg to the destination peg and you're done. So if we have 1 disk to move, we do it. If else we have more than 1 disk, we break the problem into, we move the top n-1 disks from the starting peg to the temporary peg. So we've now made the problem smaller, which is a recursive problem. We gotta move n-1s from one peg to another. We move the disk n from the start peg to the destination peg. That is not a recursive call, that's just doing some work. And then we have the second recursive problem of moving the n-1 pegs from the temporary peg, n-1 disks from the temporary peg to the destination peg. So again, you can see how we have the problem, we broke it down into one recursive problem of moving n-1 disks to the temporary peg, we move the disk, and then we move those n-1 disks to the destination peg, and we have solved the problem. The next topic is, what if you have more than one choice of what you can do when you are solving your problem? So the way to solve that is using backtracking, which is a systematic trial and error. So what you do is you try all possible decision points or branches in your problem to come up with a solution. So you try all the alternative paths, you keep going down until late, you know you can't go. For example, if you're searching a maze, you always turn left or something until you get to a dead end, and then you back up until you have an alternate choice. If it fails, you back up until you've had a choice and you try another option in that choice. And then you keep going down until you find out that doesn't fail, and then you back up until you eventually try all possible choices, and you either come with a solution or you fail. Solve the problem. The recursive algorithm for backtracking is, if you are at the solution, you're done, you've solved the problem. So your base step, you've solved the problem. You recognize that you're out of the maze, or you've defeated the bad guy, or whatever, you're done. Now, if the step you're at actually fails, you can tell that it's not, you in a dead end, or you've lost, then that set of choices that got you to that current place is not on the path to success, so return false. So you have two base cases here. One, you've succeeded, or two, you have failed. And if you have succeeded, you return true and you remember the decisions you've made along the way, and you declare a success. If you fail at this particular solution, that doesn't mean you didn't find a solution on this path, but you need to go back and try another thing. So the else is, if I'm in the middle somewhere, I check each alternative decision, and then I do my recursive solution on each alternative solution. So if you get to a success on a particular alternative, you declare success. If you find a failure by choosing that particular chance, the recursion will back out, and you'll then go to the next alternative, and you'll try search all the way down. And this works for as many decision branches as you can. This leads to some issues with very complex games like chess. There are just so many possible choices that the space of possible choices is just too large to try all possible choices. But for simpler problems, it's a great way of backtracking, because it's not a random walk. You are choosing all possible alternatives, and if the number of alternatives is small enough, you can brute force your solution. So that's the idea of backtracking. You are using the idea of recursion to remember the path you're on, and if you fail, you'll pop back out. The activation stack will pop back out to the time where you get where you have a choice to a decision, and then you try the path down for those. So, in summary, we talked briefly about how you can define data structures recursively. For example, a linked list is a node followed by a linked list, or it's empty. We'll see next week about the tree data structure. A tree can be defined recursively, and often is defined recursively. It's a very nice way of thinking about data structures, and you can also implement the methods on the data structures recursively. We can solve problems recursively, like the Tower of Hanoi. The problem itself doesn't necessarily say it's a recursive problem, but the solution is by moving n-1 disks, and then the nth disk, and then the n-1 disk, we have a recursive solution because the problem's gotten smaller. And then lastly, we can use recursion and backtracking to systematically try all possible solutions. Again, the problem is that if there's too many possibilities, we may run out of time before we get the answer. And you just can't brute force all possible solutions. But it does allow you to do some very nice reasoning on games such as chess, if you limit the number of possibilities you're going after, or as you'll see for assignment 8, I believe, the Sudoku problem, you can try all possible solutions and find out how to solve the Sudoku puzzle. Thank you very much for paying attention.